Good day, everyone. So today we are very happy to have Professor Songha Kang from Georgia Tech to give us the talk. Professor Kang works in applied mathematics, starting from variational approaches to image processing, to path optimization, fast algorithm, and data-related problems. Following a PhD in applied mathematics from UCLA, she held an assistant professorship at University of Kentucky. In 2008, she joined Georgia Tech, where her research has been supported through NSF and the SIAM-IS Foundation. The title of her talk today is Vectorization, Decomposition, and PDE identification. Songha, the screen is yours.
Thank you very much. So I would first like to thank the organizer for the kind invitation. I really appreciate this. And I'm very happy to be connecting this way. And I see some familiar names. So thank you so much for coming during this busy time. I'm also happy that we are sharing like this, but as the coronavirus got elongated, that I also realized it's very difficult to keep people engaged during the online talks. I'm sure this was the case for my students as well. So today I decided to give a relatively short talk so that just to give a main idea and then try to introduce some of the topics that I've been working on recently. Okay, so today's talk will be a relatively short talk on 3 different topics. So the first topic I'm going to talk about is silhouette vectorization by affine scale space. So this is a joint work with my student, Woo Chen Hee, who is graduating this year and who will be going to Duke as a postdoc, and Jean-Michel Morel. And the second topic I will talk about is on image decomposition. This is a joint work with Dr. Martin Huska, Alessandro Lenza, and Serena Morigi. And the third topic I will talk about is more or less related to sort of an inverse problem and in identifying the PDE. So given a discrete data set, how do we find the underlying PDE governing the behavior? I'll be more than happy to talk about any of these topics in any length or different topic as well. But today I decided to keep the topic relatively simple and just so to give an idea for that. All right, so let's get started. So the silhouette. So what do I mean by a silhouette? Silhouette in black and white is a black and white binary image. So the object of our interest is represented in black in a white background. So in between, in the transition, where there is a transition, of course, there could be a grayscale, but we're going to assume the main object is going to be black and there's going to be a white background. This image looks great, but if you start to zoom in, you zoom in the face, you start to see the pixelized effect. If you zoom in further, it gets worse. If you zoom in further, it gets worse. So when you take a picture, we cannot be free from this pixelization. Any kind of camera, any kind of phone that you have, you take a picture, you're going to be dealing with this pixelization. So what do I mean by vectorization? So the vectorization is to try to be free from this. So you are given a pixelized image. How can we change it to what is called SVG format so that it can be represented by a small number of control points? So this is called scalable vector graphics. So the main part of it is going to be given in terms of the control points, and then in between it's going to be connected. One of the benefits of changing this to SVG is it is scalable. So you can make it big or small, and you're free from the resolution. So you don't have to deal with the pixelization anymore. So if you have this freedom, wouldn't that be great? So this is one of the examples. So this is the image that I showed you earlier. So you have a face of the cat, and then you zoom in, there is a pixelization. If you zoom in further, you're going to have even more pixelization. Now, if you do a vectorization in the correct way, as you can see, this is all smooth, but it keeps the shape of it. It keeps the shape of this. The subtlety of the curve and all of the points are kept. But if you zoom in, it's all clean, because this is represented by a small number of control points like this. So it will be smooth and you're free from the pixelization. So this is what I will be focusing on. So there are a lot of related work, and I'm showing some of the citation related to this. This is not an exhaustive list, so there are more work on it. But the common method, common idea is to first of all identify the control points and then approximate the curve in between these control points. So these are general idea behind it. Another thing is the Bezier curve. At the beginning of this project, I was thinking maybe we can use something else. But in this community and in the computer graphics, this Bezier curve is heavily embedded. We couldn't really justify why we will not use the Bezier curve at this time. So we will also utilize the Bezier curve on it. So the goal is to find the good control points. Given a binary image with a silhouette, how do we find the control point? If you think about this, heavy curvature point is probably a good place to keep track of, right? Like if you imagine a box, square box, probably corners are a good place to keep. If you know the corners are corner, then you only need 4 points. So the control point near the curvature extrema will be very important. But computation of this curvature is not reliable in general. So how do we make this work? So our proposed method, you essentially have 3 steps. The first step is the computation of the subpixel curvature via curvature microscope. This work is motivated by Morel and collaborators' work on this, the curvature microscope. So what it does is that given a binary image, as I said, it could be a binary image, or in the transition, you might have some grayscale, but the main object itself is black. So now you're given a binary image, you apply a bilinear filter to it to smooth it out. However, if you zoom in, all of the pixelization, this still exists. So then we apply the affine shortening to kind of clean it out, to make it straighter while keeping the corner for it. So after you apply, so this will give you some smoothness parameter. If you do it a lot, then it's going to get rid of a lot of details, but it will be more smoother, but keeping the main corner. If you make it small, then you will keep a lot of oscillation also, but at the same time, you will keep a lot of detail as well. So after this is done, you can threshold to kind of find 2 different layers. So what is inside and outside, so essentially the boundary. But what we found out is that if you do this, there may be too many points. So it may be too many points. So as you might have noticed from the cat image even here, there's a lot of places that you can have a control point. It is really not a straight line. There are a lot of detail to it. So you can have a lot of points for it. So what do? So we wanted to because having a small number of control points will reduce the size and then reduce the complexity of the problem. So we want to reduce the control point. But if there's too many points, how do we give priority? So what are the more important control points versus what is not so important? So what are the important points? So what do is that we apply the affine scale space. So you apply affine shortening. So t is equal to 1, t is equal to 5, t is equal to 10, t is equal to 20. You keep on smoothing in a way, but you're following the curvature direction. So if you do this long enough, what you will see is that some of the points here, some of the points that you will have a lot of control points will be not as important at some point. But these corner, like really sharp corner, will persist because this is really a definite corner. So among all of the control points, now you can give priorities. What are the things that you really want to keep? So if you go to the core scale, that you can kind of track what are the important points that you really must keep. So this is what we do. So we go to the core scale and then see what persists and then backtrack it. So we backtrack along the affine shortening flow and find what are the important control points that we want to keep. So those are the points that you want to make sure we keep. Other points may not be as important. So you find the very important control points, and then we apply Bezier curve to fit between these control points. Control point and control point, you fit it. When we're fitting this, of course, there are a couple of other the steps that we added in. One of them is a deletion of subpixel extrema. Some of the times that you might, depending on the scale that you decide to keep and so on, you might have a case that the control point left to the right, two lines are the same. The tangential direction might be so similar, it doesn't really make sense to keep this point. Then we can get rid of it further. But also, if you have two control points, but sometimes that the Bezier curve approximation, we check if in between the control point, the curve of the approximation and the actual one, is it too far or not? If it is too far, we just add another control point to make it accurate. So this gives another parameter you can choose to tune. So if you want to make it more accurate or not, you can actually work around with it. So this is some of the results. So this is the original image. This is very pixelized. It doesn't look like that, but it is quite pixelized. And then if you zoom in 4 times, you will start to see 8 times and 16 times. Now, if you vectorize it, the vectorizer using our method, that you can see everything is very, very smooth. And keeping the structure, the geometrical shape of it. And then you can see the corner is very sharp. And then this sharpness can get kept. So this is the result that I already showed you. And then the CAD image is the one that I showed you at the beginning, that's showing the CAD image can be simplified and so on. So this is the saving. If this image itself is given as a PNG image or JPG, so there, because of the way that they store the image, the size is different. So we experimented with both cases. And then if you use the silhouette vectorization, then the result becomes reduced to 2. So depending on compared to the PNG image or JPG image, either you have 60% saving or an 80% saving. And then the time takes to process this takes about 0.1 second. The butterfly image that you have is 97% saving or 85% saving with the 0.15 the CPU time. The letter one with really a lot of letters, and then you can also see this will completely depend on the complexity of the detail that you have and so on. So as I mentioned, that there is a parameter that you can play around with. So meaning that if you don't really care about the detail of the object, but you do want to control the small number of control points, there is a parameter that you can play with. So this image shows that it has 362 control points, 400 and 500 control points. You can see the details, like these small details. We're zooming in this part. The small details are getting sharper when you use more control points, which is really natural, right? Because you're keeping track of the points, the definite points and so on. We also compare with the other methods for it. So the red dots here, the red dot in the boundary are the points which is given by our method. So all of the red points are the same across image A, B, and C, and D, all the same. And then the green X is given by different method, which is listed here. You can see that there are more green points, meaning they require to have more control points to represent the same image. And it is consistent for all of the method. But one method here, Harris corner detector, may seem as if you don't have as many green. So it may seem that red is even more, but notice some of the corners are actually missing. So some of the corners are actually missing in these cases. We also compare this with the state of, before that, another experiment that we did is the rotation and scaling. So believe it or not, you're given the same image, you rotate, and then you find the vectorization, you rotate some more, it actually changes. So this experiment that what we're showing is that, for example, the house, you're given a house image, you do a vectorization, and then you rotate and you do a vectorization, and then see if I can rotate it back and it matches up with the original one or not. So this will match up if this is really giving significance to the geometrically meaningful point. Because if the corners of the house, even if you get rotated, that's supposed to be identified to be the meaningful corner. So even if you rotate it and then you vectorize it and rotate it back, it doesn't match up with the original one. So these are the tests that we did. So in a different scaling also. So if you have a different scaling, then there will be different points and so on. So if you look at this graph, the blue one is our result. So some cases, there are other methods which might be better, but mostly the blue line is consistent. In the rotation case, it's even more clear. The blue one is on the top. So even if you rotate, it's very consistent. So it is giving meaning to the geometrically meaningful corner point, even if you're rotating it. Some of them really fluctuates a lot depending on the rotation, but in our case, was more or less stable. So we wanted to compare this to the state of the art because we wanted this to be meaningful for the people who's actually working on this in the computer graphics community, for example. So we compared this with the Adobe Illustrator. This is a commercial software. It has amazing power and it really has a lot of things. So we compared with that. It's really widely used, one of the most powerful method. So the red one, so this is a fish and this small part is zoomed in here. So the red part is the given image. So the red, even if it doesn't look like that, it is very pixelized. You can probably see it here. So there is a lot of pixelization already showing. So the red one, even if it doesn't show, it is pixelized image. So the yellow one is Adobe Illustrator. And then green and blue one are our method using some different parameter. We give a default parameter that you can actually use. So this might be easiest to see. So you have a yellow one, Adobe Illustrator, and this is the given image. These are the results that we get. You can see that more of the details are kept, even this small opening, which deleted, and then small dots here, which was deleted, and so on. We can do this more quantitatively, so we can actually plot this graph. So we did it many, many different times with different parameter. So this blue line is using Adobe Illustrator, and this red one is our method. So what you're looking at is the bottom part. The bottom part is the accuracy. So this is a intersection of two objects. So you mean the true one and the vectorization one. So the whatever is overlapping over each of them. So the more accurate it is, it's going to be more closer to the one, the value one. So the more detail that you keep, it's going to be closer. But in order to keep that much of an accuracy, there is a number of control points associated with that. So for the same amount of accuracy, for example, then our method gives much less number of control points. The black dot here is the default that we propose. This is the default that you can play around with in a general sense. But AI, AI meaning Adobe Illustrator also has its own parameter. So we did play around with this. It's really it works quite well. And it is really, the accuracy is quite high, 0.95. So even if you play around with it, our method can go even more accurate. So even more accurate for that. So using a very simple method that which we already know, the affine scale space and the curvature extrema, that we can actually get something quite meaningful for that. Okay, so let me move on to the next topic. So if you have any question, please feel free to ask in the chat. Okay, so otherwise, let me move on. The next topic I want to talk about is image decomposition. Image decomposition has been around for a very long time, and a lot of people has worked on this. This particular project was motivated by the piecewise constant and harmonic term. So this was thanks to Dr. Huska visiting Georgia Tech for a couple of months. So this is the starting point of it. So when we want to separate the image like this, you have a gradually changing intensity, and then there's a piecewise constant. We can try to replace our TV-like term to be this non-convex term phi. And then the smooth part will go to the W here. So it's a L2 norm of the gradient of W. And this particular decomposition was done by F is equal to U plus V, U plus W. this actually works quite well. The reason why it works quite well is because this phi function, which is non-convex, has a particular shape like this, which enforces the sparsity of the jump even more. So you want this to be really pushing the limit of being piecewise constant. So piecewise, you don't want to have a stair. You want this to be like straight. So you want to make it sparse as possible, the jump as sparse as possible. So in these cases, in practice, it works well. And it does have one parameter A that which can change the shape of this. So it can be a little bit further off, or it may be really sharp. So it kind of moves around. So you have a parameter for that. So it really works well in the piecewise constant. I was actually surprised to see it. But one of the issue was that with a small amount of noise, it doesn't mess up the whole decomposition, but it will all go to harmonic part. This small amount of oscillation or small amount of noise will mostly go to the harmonic part. So these decomposition, when you have a non-convex term, which really enforce the sparsity of the jump, I believe that it is really too strong. So it is very strong. So everything else is gonna go to the other side. So the non-convex term is so strong that everything ends up. So what do? We give a place for it to go. So the easy solution is to add another term for it. So the G-norm. So image decomposition has been explored extensively, and there's such a beautiful work on this. So this is already started like 20 years ago now. And this is how to capture the oscillatory part. So the beginning model was starting from the total variation and the G-norm, and different type of approximation to G-norm has been explored. This is, I'm giving you a reference, but this is again, not exhaustive list of it. And yes, and so yes, it is not exhaustive, but just some of the example for it. And in this particular setting, that we decided to use the Auger-Soleil-Vessey for the H-1 norm. So this is what we decided to use. All right. So this is the proposed idea that we've been exploring. So what do we want to do? Our objective is to separate the image F, given image, to piecewise constant, smooth part, and the oscillatory part. Piecewise constant part, we want to keep this sparsity enforcing the piecewise constant. We want this to be even stronger than the TV. So it's a little bit pushing it. But the smooth part, before it was a gradient of the L2 norm of gradient, but we use Hessian for this. And then you have a G norm. So we have a non-convex term, and then we have a smooth term, and then we have a G norm, which is the same idea as Auger-Soleil-Vessey, and we use a negative Sobolev. What is the idea behind it, and how do we make this work? This is actually much more subtle than what I give impression to right now. The reason is this. Let me give you some intuition. So if you look at images like this, the first set of image is just piecewise constant. So it's piecewise constant image, and from left to right, I am making the scale smaller and smaller and smaller. So you have a big one, and then it gets smaller and smaller. As you can see that as it changes from left to right, it almost becomes more texture-like, more detail-like. So if you look at the actual value, the norm itself is smallest for the non-convex term. This is smallest because piecewise constant, and then it increases at some point because it starts to behave more like a texture. But if you look at the text genome part of it, the texture part, now they start to reduce only when the image itself looks more like a detail. So there is a subtlety of this change. And also, if you have a blurry image, the first term is going to be terrible because there's no piecewise constant, right? So they don't like it. So the value is going to be very big. So the top row is very big. but the harmonic term loves it, right? So this is, oh yes, this is so smooth. I really like it, right? So the second one is very small. And then the genome part of it, as you can see here, this value is pretty big. And then it starts to reduce because it becomes more texture-like. So when we even experimented with the texture itself, like, noise itself, it's completely noisy. Yeah, the first term is unhappy. And the second term, they thought I was sort of happy at the beginning, but it starts to get unhappy. And then, but relatively, the genome stays low. So as you can see, there's a three term which is trying to do their best in their own way. So the main question is, how do we balance them? How do we balance it so that it will work together to give the answer that we want? So this is why it is much more subtle than you expect. So what we did was this. So we wanted to make sure that these three terms are as separated as possible. So even we had like the gradient term, but we changed the Hessian is because we wanted to make sure that this has less overlap in between each other. There seems to be a question, but I cannot see it. Sorry. I think I can see the chat, but I don't think I can see the question Q&A for some reason. Okay. So now you have, so we wanted to separate. So we have a term with phi 0, the non-convex term, but we wanted to have a minimum, well, possibly small intersection between these two, and then also the noise term. So we picked it so that this is a histogram. We're plotting a histogram of V and W and N, and we wanted to make sure there is some gap in between. Depending on the image, depending on the noise, depending on the detail of the image, of course, this may not be perfect, but still, this is the idea. And also, we have three different terms. We have three different terms. How do we balance it? So the way we balance is the first term. In front of first term, there is a coefficient gamma 1. The second term has gamma 2, gamma 3, and then the third term has gamma 3 and a fitting term. But we want to make sure that this whole term is gamma 1 times R1 and gamma 2 times R2, gamma 3 should be more or less balanced. We didn't want to give priority to one or the other. So how do we do that? And then also we have ADMF scheme for the numerical computation to actually show you. Okay, so we can do it. So the estimation that we do is we play around with these particular regularization terms. The phi 1, the non-convex term has a shape something like this. And then you have a second term which looks like this, right? So you have a different behavior. But we can find your A bar and T bar, which is the smallest jump that you have for A bar, smallest jump in the piecewise constant case. And then you have the maximum of the smoothness of it. Those should be the transition point from distinguish between the noise and smooth part and the piecewise constant part. So we can choose this point as an intersection point. So whatever is smaller than that will be captured in the W part. Whatever is bigger one is going to be captured in the piecewise constant part. So we have a way to separate this. For the noisy one, so the noisy part, it is actually harder because we can try to analyze it. So what the direction that we took is we wanted to have some statistical estimation of what this value of R3 should be, and then we backtrack from that. So this is how we got this number. Statistically, when we were looking into it, there is a slight detail, which is the direction, the derivative in terms of both direction correlated or not. This is estimated assuming there's no correlation between them. So this is the estimate. So now we have a good estimate on how to pick the parameters and then how to make sure that these three terms are all working in balance. So let me show you some results. So this is an input image F. There is a spotlight in the corner. So now the piecewise constant part is captured like this. And then this is the harmonic part. And this is the texture part. And this is the input, the piecewise constant part. harmonic part, gradually changing the color, and the texture part. As you can imagine, this will work very well for the cases like a shadow removal, right? Because the objects are there, the objects are object, but the shadows are smooth. The shadows are smooth. So if you have an input image like this, we can separate this. So this U image is just getting rid of the noisy part. And then this is the piecewise constant part, which keeps all of these shapes of it. And then this W keeps the wave. And then there's a noisy part. So you can apply to this image also. So there is a cylinder, and then you have a shadow. So this is the piecewise constant part, and this is the harmonic part, and this is the noisy part. If you look at the harmonic part, it really has the shape of the cylinder, and then the shadow also. You can apply to images like this, which there is a shadow covering some of the one of the poster. So then it can separate to be a piecewise constant, and then the shadow part of it. We can also apply this for the spotlight removal. So you have a noisy image like this. You can get rid of the spotlight. So this one is piecewise constant. And then this image is the spotlight. So the piecewise, this is smooth part. And I'm not showing the noisy part of it, but you can imagine the noisy part by this one. So this image is without noise. This is the noise one. And then the SNR compared to the original image increased because the noisy part is separated to the noise component. Any questions for now? Okay, great. So let me move on to the last topic for it. All right, so one last thing that I wanted to show you is the identification of differential equation with the numerical technique. This is the joint work. I think I might have forgot to mention this. Joint work with Wu Chen-hee and Hao Liu, who is going to Hong Kong and who was a postdoc at Georgia Tech, and Professor Wenjing Liao and Professor Yingjae Liu at Georgia Tech. It's been really fun actually exploring all of these topics, and I really I cannot thank the collaborators enough. It's really been a fun time for all of the topics. Anyway, so the last topic that I want to talk about is identifying differential equation with numerical techniques. So what it does is this. Given a time-dependent discrete data, so the only thing that we have is discrete data, which is non-continuous data, but it is time-dependent. So there's some time information to it. We want to find the underlying PDE governing this behavior. The actual motivation for this is that I wanted to take a video with my phone, some behavior, and then the phone app will give me what equation is going to be. So that was what I wanted to do. Of course, as a person doing image processing, I know this is a very difficult problem to do. But still, first things first. So let's say we're given a discrete time-dependent data. Can we at least find the PDE? So the assumption, the easiest assumption that we can make is the underlying PDE can be expressed in terms of sum of all of these discrete terms. The terms could be nonlinear, u square, ux, ux square, or ux, or uxx, and so on. For this work, we only consider up to second derivative, uxx. So uxx square is there, but still uxx. I will explain why that this is the case. So if we assume, even with the nonlinear term, if we assume that it can be expressed as an addition, then you can write it in a matrix form. So F keep tracks of all of the term, the differential term, u, ux, or u square, or so on, each of the term. The coefficients are the one which is either 0 or some value. So for example, you have ut is equal to uxx. Everything is going to be 0 except for the 7th term. So the vector that we're looking for is 0 and some number, and then everything will be 0. The B part is the UT part. So UT, and so that part is the UT approximation and F and A. As you can imagine, naturally, the sparsity plays an important role here. So of course, there are a number of works. Again, this is not an exhaustive list, but these are some of the work along this direction. And so there are some physically motivated work, but in mathematical point of view, a lot of the work has been stemming from the sparse regression. As you can see why, right? And also recently there are some deep learning type of approximation. So like train the network to find and so on and so forth. A lot of this work, majority of this work or a lot of this work, one of the issue is noise. So one of the issue is noise. If you have small amount of noise, if you're training the noise or something, so the noise has been some of the big problems with it. So some cases you have to avoid having noises, or sometimes you need to have a particular type of noise and so on. So we wanted to design a method that which can handle noise and also the boundary condition. We wanted to free up the boundary condition. It could be durational boundary condition, it could be Neumann boundary condition, it could be periodic boundary condition. So some cases, periodic boundary condition works so much better, of course, because you have more information. So if you change this to durationally or a Neumann boundary condition, it gets harder. So we wanted to free up. So this is what we propose. So given discrete data, we build a feature matrix. So F as well as your B, which is UT, using numerical approximation. We use ENO scheme. So ENO scheme, essentially non-oscillatory scheme. My shout out to numerical analysts. Anyway, so we use ENO scheme for, in this particular case, we use fifth order polynomial because we wanted to guarantee at least second order for the second order derivative. So because this is a very sensitive problem with the noise as well as the order of the differential term that you have, so we want it to be consistent. So we use ENO 5 to approximate the derivative term. And after that, in this work, we did use lasso, L1 minimization. L1 minimization itself is non-crucial. It is not crucial. But it really helps reduce the number of computations that we do. Anyway, so we do an L1, and then we get some possible candidates term. And then after that, from these possible terms, we collect them in a combinatorial way, all possible case, and then we check the time evolution error. And then whatever gives us the smallest error will be our underlying PDE. So what do we do is that you have a candidate and then we compute different equation and let it evolve. The reason behind it is this. So the motivation behind the time evolution error. So as I said, that L1 can be skipped, but it will be really heavy computation, but it can be skipped. The reason why we believe we need more than just having a L1 minimization is some of the zero coefficient may come non-zero some of the times. It will depend on the thresholding and it will depend on the choice of lambda. There are subtlety to make this to make this work, so to use it. So we compensate by, or our main motivation is the time evolution error. There's two fundamental idea behind this. Number one, in the PDE identification, wouldn't that be wonderful? You can say this term, you're either yes and no. Yes, you're yes and no. Per term, if we can determine you're in, you're out, that would be great, right? But it doesn't work like that because the nonlinear PDE is nonlinear. You have a behavior feeding, influencing the next time. So you cannot identify term by term in any ways. So you need to work it as a set because this is nonlinear PDE. So you have to work as a set and see if this set makes sense. So this is why we're doing time evolution. The fundamental idea behind it is the numerical convergence. The numerical convergence, right? This is what we learn in numerical PDE. If you have a consistent and stable method, then if you change your delta t to go to 0, this will better go to the original equation. This is the fundamental of numerical convergence. So this is what we use. So when you have a candidate term, we evolve this with a smaller delta t. Smaller delta t, well, we just do it once with the small delta t. But the smaller delta t it gets closer to the equation that you are trying to mimic. That will be the best thing. So we have a candidate one, you evolve this with a smaller delta t and see if it actually matches the data that which is given to us. So this is how we check. So as a set, we evolve. As a set, it needs to be evolved. And then we want to see that it actually matches up with a smaller delta t. Let me show you a very, very small, the introductory example for this. This is how we test it. We started out with a Burger's equation with a Dirichlet boundary condition. In this case, we know analytic solution. We have a true analytic solution. So we just took it and then we just sampled it. Okay, you sampled it with delta t, delta x and delta t something. This has no noise. So we even know the true data. So from the true data, the discrete time-dependent discrete data is given to us. If you apply our method, then U and UX were picked after the L1 in this case, the lasso, we just use lasso. Then you have two terms. So you have three different equations you can build. One is UT is equal to U, like that. One is UT is equal to UUX. One is this equation. The coefficient is computed by the least square. We just fit it. Among these three choices, the red one has the smallest time evolution. So if you shrink delta t, just evolve it, and then you will see that the error is getting smaller. So it is closer. This is how we pick the right one. So the right equation has been picked with negative 0.99 as a coefficient. The true solution was -1. In these cases, as I mentioned, noise plays a significant role. So we did look into this noise very carefully. So the finite difference and also the order of the accuracy, also the measurement error, and then you have a downsampling. There are a lot of things getting involved with generating this noise, and then noise does make it very difficult. Also from the term itself that you can see, if you have a higher derivative, then it gets harder. And then on top of that, when we generate, in order to do an experiment, we downsample this. We add noise and then we downsample it. And then so given the noisy time-dependent data, can we identify it? So the higher order it gets harder to identify. And the more noise you have, of course, it's going to be difficult. So this is one of the examples. This is one of the recent work we did on successfully denoised diffusion. This is one effect that I can show you. Well, I mean, this is one example. So you have a sine function, which has a noise, then it looks like this. You take the first order derivative of this discrete data because we only have discrete data. So the best that we can do is to approximate this in the best way. That's why we use ENO5, but that's all we can do. But if you take the first order derivative, the noise gets emphasized. You take the double derivative, it gets even more emphasized. So these black lines are how the true data should look like. The red one is the oscillation that you actually get. So in this case, that we denoise it. So we denoise this by moving least squares, and we do it denoising and differential. You take the derivative to have an approximation. We denoise it, and then take the derivative to denoise it and denoise. We successfully denoise it. There's a theorem that we can show that under some assumption, the assumption meaning the polynomial, the approximation when you're using the moving least square has to be at least s degree. And then the differential, when you're taking a differential operator, that we need to make sure that order has to be as high as that. If you use a very simple differential, then you will mess up with the order of accuracy. But if you are taking a differential operator in a correct way so that it will be at least S order, then you can guarantee the accuracy for it. So even if we are doing this successive denoising, that you can guarantee that it will have the certain degree of accuracy. So we further refined, rather than using the lasso, we moved on to using the subspace pursuit, but the subspace pursuit require the knowledge of the sparsity, but we don't know that. So we did it with k is equal to 1, k is equal to 2, all different levels of sparsity, but get the best one. And then we pick the best one by using either cross-validation or time evolution error. The time evolution error, before we did it from beginning to the end, now we multi-shoot. From the multiple place, we shoot together and add up the error. It's the same idea, it's like a multi-shooting. So we do the multi-shooting and add. So rather than adding this red one at the end, we're adding these small red ones to shoot it from the smaller window. The reason is some of the time the PDE itself may become unstable. The PDE itself might become unstable. So this will actually make the method more stable. So this is some of the results. So in the transport equation, let's say the original equation itself was ut is equal to negative u. In no noise case, they relatively do a good job on it. You had 10% noise. Without denoising, the results are pretty bad because the terms are not even the same. But if you use the denoising, the result is negative 1.03, where the true solution is negative 1. We can even do it for 30% noise with negative 0.9 as a coefficient. So these shows the coefficient error for each time. And also you can do this for the Burger's equation with diffusion. As I said, when you have a diffusion term, it gets very difficult to identify, but it actually does pretty good job leading up to the 5% of noise. We can do this for a third order, so we did it for the KDV. Okay. All right, so just to summarize, so I gave talk on 3 different topics on it. So in the silhouette vectorization using the affine scale space, so it is really comparable to the state of the art, and we are using some affine scale space and the curvature microscopes, like some of the things that we are familiar with. The result looks great, and we are extending this to the grayscale and color images. You can imagine that it suddenly becomes very complicated because you have to deal with a different color and then all of the different the boundary that you need to keep track of. So this is what we're working on. The second topic was an image decomposition model, that we propose a model which is piecewise constant and smooth and then oscillatory part. So there is a balance between these 3 terms that we explored, and then using the good balance that we should be able to get a good result. The A also, there is a parameter that you can tune. So the one part of the ADMN can be convex at least. So there are some details that I didn't talk about today. Also, recently we reworked on the mathematical analysis of this model as well. So the third topic that we talked about is identifying differential equation with numerical techniques, and it is robust against noise. And it can identify, I didn't show you today, but it can identify nonlinear PDE with varying coefficient also. And we've been extending this to non-local PDE and some other methods as well. Okay, so this was based on some of these work, and that is it for me. Thank you for your attention, and thank you for coming during this very busy time. Thank you very much.
Thank you, Songha, for this very interesting and diverse talk. And now it's the question and answer time. So if you have question, you can either type it in the question and answer box or chat box, or you push the raise hand button, and I will invite you to speak directly to the speaker. So I have one question already in the question and answer box, and maybe I ask Ashwin, you want to ask directly? So Ashwin, so you can unmute and then you can ask directly.
Okay, thank you. Can you hear me?
Yes.
Yeah.
Okay, great. Yeah, hi Sungha, this is Ashwin. I mean, I've done some work on discovering PDEs in the past, and the work that you presented was very interesting. But one common problem that we face, particularly when trying to discover PDEs that could be parametric, and also PDEs where the boundary conditions are the ones that actually contain the parameters. Can you also infer or discover the boundary conditions through your method? And the reason that is important is because, I mean, the boundary conditions is what primarily uniquely identifies the solution. So sometimes it's important to actually learn that also. And then once you have that, you can actually construct maybe reduced order models with the discovered PDE that you do with your method. So that's why I was curious if you can discover the boundary conditions also.
Oh, that's a very good question. So yes, so in the current setting that we didn't explicitly look for the boundary condition. So here, like, so I think what you're asking is that is there a behavior that which is actually governed by the boundary condition, right?
Correct.
I think that's what you're saying. Yes. So we have not explored it directly. So we have explored in a different boundary condition how we can actually identify it. But our focus was not to look for the boundary condition itself. But I think that's a very good question. Yeah, maybe we should look into this. I think this is a very good question. I didn't really we didn't really heavily experiment on the parameter which is given from the boundary condition. But I think that's a very good question. I think there yeah, I think there might be a way to do, but we might have to reduce some of the condition, as you said.
Okay, thank you.
So, are there any other questions or comments? So, Song, I have a question. So, for the last topic, I'm think I a little bit lost because so when you determine the equation, right? So you solve this system, okay, and then you determine the equation, and then you also change the delta t to determine whether it's good or it's true, right? But then later on, then you say that actually you don't separate into two steps, right? You build it in inside the iteration like a shooting method. Am I correct? So it's not separate in the two stage, right? So it's mixed up, right? Am I correct?
Oh, I see. It is still separated because you have a candidate point, and then we need to still test it. So the testing part, we do it with a smaller delta t. To get the time evolution part, it is separated. So now you just use to match it. So that part is it's still separated. Does that make sense? Let me explain it like this. So first we do, let's say, so this is not the right one, but let's say in the step 2, that there is some sparsity constraint that it gives us some of the candidate points.
Yeah.
So in the candidate points, every time we want to check if this is valid or not, this is when we work with a smaller delta t to get the time evolution error.
I see. So it's already built in step 2 then.
Yes, so it is built in step 3. So step 3 is the part that whenever we want to evaluate the time evolution error is the only time we use the smaller delta t to evolve.
Okay.
So that is part of the evolution error. So the computation can be heavy. So in the multi-shooting cases, we can do it in a parallel.
Okay. Any other questions from the audience? Yeah. Maybe I ask one more question. So for the middle part, the decomposition. So what if so now of course you have this well kind of piecewise constant image, right, with some harmonic background and then some noise. So what if I have some image that have well piecewise constant, but then the edge are not that sharp? Then what will happen to your method?
That's a very good question. So it could be something like this. It depends. So then you might consider this the smooth part might take over.
I see.
So if you just have something like this, then they will try to separate this to be smooth parts. The smooth part will make it smooth, and then they will do their best to find the piecewise constant part.
Okay.
So the smoothness, the edges are not as sharp. It's sort of like a de-blurred case, the blurry cases. So then the blurry part will be taken care of with the harmonic part, and then the other part will try to be piecewise constant.
Okay. 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 So any other questions? If not, then let's thank thank you, Sungha. And so yeah, okay, Eric, you have a question. Maybe you can ask, right? So I don't have to unmute you.
Right. Thank you, Songha, for your talk. It was very interesting. Can you say a little word about what you called a fine shortening in the first part of your talk? Is it something related to some kind of mean curvature flows, to
Yes,
singularities? Could you say a little word on that?
Yes, of course, yes. So this essentially what we need to do is that just curvature enforcing. So this is just affine shortening. We didn't invent this. So following the direction, so you have a normal and tangential direction. So you want to just enforce the direction of it. So you keep the corner. So it can be used, different method can be used, but we needed something to keep the corner while smoothing it so that it will move. But this was the just affine scale space. We didn't invent this. This is one of the well-known methods, which just keeps the direction of it and then just sharpen it. So if you do more, eventually it will come down to be a circle and then it will disappear because if you evolve a lot. But if you don't do it enough, like you just do it at the beginning just to see how behavior goes, then it will keep the sharp corner of it. But eventually, yes, like the mean curvature flow, it's gonna just go into a circle and then it will disappear.
And because you're starting with a grid that is pixelized, would it make sense at this stage to use some anisotropic mean curvature flow?
Yes. So in this case, that we started out with taking out the boundary first. So we made this as a contour first and then applied to it. We didn't do the image directly. We actually took out the boundary point first. Then it becomes a curve evolution. So then we applied it to that. Was that your question?
Well, my question was more related to, because your original image is based on a Cartesian grid. The examples you showed. Would it make sense to use anisotropic mean curvature flow to discriminate this direction of the grid?
Oh yes, but when we are computing this, we actually do it like that also. So we don't do this as a Cartesian base. Yes. So we already incorporate that to be anisotropic. Yes.
I see. Okay.
We don't do it as a grid base. No, they're not X and Y, but we do follow the normal direction of the curve and then the curvature direction of the curve.
All right.
Maybe that was your question. Sorry.
Okay. Any other questions, comments? If no, then thank you again, Sungha. Okay. Okay, and good day for everyone.
Yeah, thank you very much for coming. I think we're getting really tired with this online seminar, so I hope I kept you entertained. So it was good to see everybody. Thank you very much.
Thank you. Thank you. Bye-bye.